Hey everybody, I have shared with you a worksheet that has some stoichiometry practice problems, including some limiting reactant problems. And I wanted to go over a few of those problems with you here in this video format, show you a little bit about the process and sort of think through aloud how I would solve these problems, and hopefully that will help you get a leg up on doing some of the problem solving yourself. If you feel like you can tackle these on your own without the help of this video, by all means, hit the pause button right now and give it a shot. But if you've already tried and you're feeling like you need a little help, then let's take a look. The first question is directing us to what is a very important chemical reaction in industry. It's the production of ammonium sulfate, one of the key components in a lot of fertilizers. So this is made on an industrial scale by chemical companies. And the chemical reaction is already given with the formulas for the two reactants, ammonia, NH3, and sulfuric acid, H2SO4, and the product ammonium sulfate on the right side of the reaction arrow. And it's balanced, and it's a simple 2-1-1 ratio of reactants and products. The first part of the question asks what mass of ammonium sulfate is produced if 50 liters of ammonia gas reacts completely at STP. So we are given the amount of just one of the reactants, ammonia gas, and we would therefore conclude that there must be more than enough of the other reactant, the sulfuric acid in this case. So we're doing a calculation with the given amount of ammonia to start with. And here's what that would look like working that problem out. We have our given quantity of the NH3, the 50 liters. In order to find out how much of the product could be made, we need to go through moles so that we can connect with that mole-to-mole ratio in the balanced equation. So we're going to have to convert our liters of gas at STP to moles. That's done in the first step here. And then we can use the molar ratio from the balanced equation to change from the moles of ammonia, NH3, to the moles of ammonium sulfate, the product in question. And there's that step in the middle. Now the last thing we need to do, since the question asks for the mass of the ammonium sulfate, is to convert what would now be moles of ammonium sulfate into grams, and that requires the molar mass. If you haven't already figured that one out, the molar mass is given there, 132.17. And plugging all that into our calculator, we would do the 50 liters times 1 times 1 times 132.17, and divide all of that by the product of the denominators, 22.4 times 2, and the final answer, taking into account significant figures, is 148 grams of ammonium sulfate. Part B asks what mass of sulfuric acid is required to react completely with the 50 liters of ammonia. So they want to know what would be the minimum amount of the H2SO4 that would be required to go with that 50 liters of ammonia. And here's the solution to that question. Another pretty straightforward stoichiometry problem where we are starting with liters of ammonia. That's the liters of gas at STP. So we know that we have the 22.4 liters per mole gas at STP ratio that we can connect liters to moles. Once again, using the mole-to-mole ratio for from the balanced equation, 2 moles of NH3 for every 1 mole of H2SO4 up there. So that gets us to the moles of sulfuric acid and then we need the molar mass to get to the grams that was asked for in the question. Question asked for mass, so we need grams. And plugging all those numbers into our calculator, 50 times 1 times 1 times 98.09 divided by 22.4 divided 22.4 times 2, 109 grams of sulfuric acid would be needed. Okay, moving on to the second question. It's a combustion reaction where propane, C3H8, is burning in oxygen. And like all combustion reactions where there is a carbon-based fuel, the products are going to be carbon dioxide gas and water vapor or steam. And the first part asks us to write the balanced equation for this reaction, write the equation, and then balance the equation. So the C3H8 is given. I think most of you know now that oxygen gas is O2, CO2 for carbon dioxide, and H2O for water vapor. So when we map those all out and finish balancing the equation, we get 1 mole of propane reacting with 5 moles of oxygen, yielding 3 moles of carbon dioxide and 4 moles of water. And you can count up all those atoms to make sure I got that right. The second part gives us a mass of propane that is burning in excess oxygen. So not a limiting reactant question again, because we are only given the quantity of one of the reactants. So we have 5 grams of propane burning. What volume of carbon dioxide gas is produced at STP? So if we were using that sort of roadmap for the stoichiometry problems, we're starting off with grams of our reactant, and we are going to a gaseous product, in this case the CO2, and they're asking what volume would that be at STP. So if you're using that roadmap, you can find where we're going to start, where we're going to end, and let's look at the stoichiometry. So there we have our grams of propane starting off. First step is always to convert to moles. In this case, we need the molar mass of C3H8, 44.1 grams. Using the mole-to-mole ratio from the balanced equation, we can switch from the given propane to the compound that the question is asking about. That's our CO2. That's a 3-to-1 ratio. And then the question is asking for the carbon dioxide in liters at STP, so we use our molar volume of gas equivalent, 22.4 liters per mole, and punch those numbers to give us 7.62 liters of CO2. Part C asks us about the water vapor. If 75 liters of steam or water vapor are produced at STP, what mass of propane must have burned completely in the oxygen? So we're starting with the volume of gas this time, 75 liters, and using a liters to grams conversion on our roadmap. And that means first step, using the molar volume, 22.4 liters per mole to get us to moles of the water. 4-to-1 ratio from the balanced equation converts that moles of water to moles of propane. And then there's that molar mass for C3H8 that we used in a previous part of the problem, and punch our numbers, do our order of operations right, and we get 36.9 grams of the propane would have burned to produce that amount of water vapor. All right, the third question is fermentation. And there are different types of fermentation. This is alcohol fermentation, where ethanol, C2H5OH, is one of the products. Carbon dioxide is the other product in this type of fermentation. And fermentation can happen with lots of different types of sugars. This reaction is giving us the sugar glucose as the starting point. That glucose is broken down by this process to yield 2 moles of ethanol and 2 moles of carbon dioxide gas. So we're going to have a few problems that deal with this balanced equation. The stoichiometry is pretty simple there, 1, 2, 2, but you may need to pause the video and come back to see this because the questions are in another part of this handout. So the next part of the question is asking about what mass of ethanol would be produced if we started off with 5 kilograms of glucose and it decomposes, ferments completely. So we're given a mass, and it's asking for a mass, so that's a mass-to-mass stoichiometry problem if you're using the roadmap. One extra step, because we're given a quantity in kilograms, and because molar masses are calculated in grams, we want to start off by converting the 5 kilograms of glucose into grams. Now, you may immediately recognize that that's 5,000 grams, and if so, that's great. And if not, there's the conversion factor to get us to grams. And then it's just a case of grams to moles in this step, using the mole-to-mole ratio to convert from the glucose to the ethanol, and then going back to the grams because it's asking us for the mass of ethanol. And then we need the molar mass. And there it is, 46.08 grams per mole of ethanol. And if we punch our numbers in correctly, that's going to give us 2.56 times 10 to the third grams, or 2,560 grams, or 2.56 kilograms. Part B asks what volume of carbon dioxide gas would be produced if only 100 grams of glucose reacted completely. So we're looking for a volume at STP. That's our target. And we're starting with 100 grams of glucose. That's where the calculation will start as we do our problem solving. And here's what that calculation will look like. 100 grams of glucose, converting that to moles first, using the mole-to-mole ratio from the balanced equation. Whoops. Using that mole-to-mole ratio. Now we're in carbon dioxide. If we stopped and calculated, we'd know moles of carbon dioxide that were produced, but the question asks for the volume at STP, so we use our molar volume, 22.4 liters per mole, and punching that in gives us 24.9 liters of CO2 would be produced in that reaction. Okay, and the last question I'm going to go over with you from this set of problems is the one, number 4, that is considering the reaction between zinc metal and hydrochloric acid. First, write the equation for this reaction and then balance the equation. So this is a single replacement reaction, and I wouldn't expect you to know what the formula for hydrochloric acid was. So if I gave you that formula was HCl, then I would expect you to be able to write the equation for this reaction, because you should know that zinc metal, just pure zinc, would be Zn. And if it's a single replacement reaction, once you write down the zinc metal plus HCl, I'm hoping that you might be able to guess what the products are. And indeed, those products are hydrogen gas and zinc chloride. The zinc is replacing the hydrogen in HCl. The element replaces a like element in the compound. So we wind up with zinc chloride as one of the products, and then the hydrogen gas on its own as the other product. And then that's a simple balance, just the 2 coefficient for HCl, and we're good. Part B asks us to calculate the volume of hydrogen gas that would be produced at STP if 25 grams of zinc reacts with 25 grams of hydrochloric acid. This given of 25 grams of one reactant and 25 grams of the other is the clue that this is a limiting reactant problem. So it doesn't say up front in this question that it is a limiting reactant problem, but because it is not specified which reactant is limiting or excess, we're going to have to figure that out by doing some stoichiometry. So remember, the general plan or strategy for doing this is to take the given quantities of both of the reactants and calculate how much of one of the products could be produced. If the question is asking particularly about one of the products, then that's the one you should find out about. So in this case, the question is asking about how much hydrogen gas would be produced. So we're going to take our 25 grams of zinc and calculate how much H2 gas would be produced, and then take 25 grams of HCl, the hydrochloric acid, and calculate how much hydrogen gas could be produced from that. And once we've done those 2 calculations, we ought to be able to interpret those results and determine the limiting reactant and determine what is the theoretical yield, the expected amount of H2 gas we should be able to get from that reaction. So we can see those 2 stoichiometry calculations mapped out, starting with the 25 grams of zinc, converting the grams to moles, using the mole-to-mole ratio of zinc and hydrogen gas from our balanced equation, 1:1, and then the 22.4 liters per mole for the molar volume of a gas at STP. Theoretically, from that amount of zinc, we could get 8.56 liters of hydrogen gas. Same kind of calculation with the 25 grams of HCl, grams to liters on our roadmap. First converting grams of HCl to moles of HCl, then the mole-to-mole ratio, in this case 1:2, and then the molar volume of gas, 22.4 liters per mole, and we wind up calculating that with that amount of HCl, we could get only 7.68 liters of hydrogen gas. So that is the theoretical amount of hydrogen gas that could be produced. Part C says identify the limiting reagent and the reactant that is in excess. The HCl must be the limiting reactant because the stoichiometry tells us that that amount of HCl will produce less product than the given amount of the other reactant, the zinc. So HCl is the limiting reactant, the zinc is the excess reactant. And the last part, Part D, asks to calculate the percent yield if 6.53 liters of H2 gas are actually produced. So we did the stoichiometry up here and determined that theoretically we should get 7.68 liters of hydrogen produced from that 25 grams of both reactants. But reactants rarely go all the way to completion, and there are a whole lot of other things that can go wrong, as we've experienced in lab sometimes this year. So not that surprising that you get less than the expected. The percent yield is just the observed value, how much we collected, 6.53, over the expected value, the hypothetical or theoretical value, times 100. That's an 85% yield. And that's all I'm going to say for now. I hope you can do the other problems on your own. Thanks for sticking with me this long. See ya.